Our galaxy is a gallery of cosmic impossibilities. For centuries, we thought we understood the basic rules for building a planet, but the discovery of worlds beyond our sun has rewritten the book. Modern telescopes have not just found new planets, they have unveiled bizarre and inexplicable phenomena that defy the very laws of physics and astronomy we once took for granted. By staying until the end, you will witness 25 of the most puzzling anomalies ever detected, each one a mystery that stretches our imagination to its limit. How can a planet be denser than steel yet lighter than cotton candy? And what does a world with permanent metal rain look like from its surface? When you look at the stars tonight, what kind of impossible world do you hope is hiding in the darkness? The first of these cosmic puzzles is a world of unimaginable wealth and unimaginable violence. It orbits a star you can see with the naked eye, a sun-like star called 55 Cancri, just 40 light-years away. The planet is 55 Cancri e, and it is not a world of rock or gas, but of carbon, crystallized under immense pressure into something extraordinary. This is a super-Earth, a planet several times the mass of our own, yet its composition is utterly alien. When astronomers analyzed the light from its parent star, filtered through the planet's thin atmosphere, they found something shocking, a glaring absence of the chemical signatures for silicon and oxygen, the very building blocks of Earth's rocky crust. Instead, the evidence pointed overwhelmingly toward carbon. This means the planet's surface is likely not granite or basalt, but a dark crust of graphite, the same material in your pencil, overlaying a planetary interior where pressure transforms that carbon into something far more precious, a diamond core that could be thousands of miles thick. Imagine a landscape that glitters with a cold, dark luster under the light of its close, blazing sun. But this is no serene jewel box. The conditions here are a form of planetary torture. 55 Cancri e is so close to its star that one entire year, one full orbit, takes only about 18 of our hours. This proximity locks the planet with one hemisphere forever facing the stellar inferno. The dayside temperature soars to nearly 4,300 degrees Celsius, hot enough to vaporize iron and melt steel. The very rocks would flow like liquid, and any diamonds on the surface would not sparkle, they would glow with a hellish incandescence. It is a world of profound contradiction, a treasure of cosmic proportions forged in a furnace of apocalyptic fury. What other impossible substances might be hiding in the hearts of distant worlds? While one world glows with the heat of buried diamonds, another stares with a single, unblinking eye into the abyss. This is the story of Tau Boötis b, a gas giant locked in a gravitational embrace so tight it has lost its spin. The phenomenon is called tidal locking, and it is as simple as it is terrifying. Just as our moon always shows the same face to Earth, this planet has one hemisphere that permanently faces its star and one that is forever turned away into the cold dark. The result is not a world with a day and a night, but a world cleaved in two by a permanent line of twilight. On the day side, under the constant, unfiltered glare of its sun, temperatures rage hot enough to melt lead, a searing desert of perpetual noon. On the night side, in an endless, star-filled midnight, the cold is so profound it approaches the chill of deep space itself. This is a planet of absolute extremes, a cosmic coin frozen mid-flip. Yet, in that razor-thin border between fire and ice, scientists speculate a sliver of possibility could exist. This is the Terminator line, the Twilight Ring. Here, the furious heat of the dayside battles the deep freeze of the night side, potentially creating a narrow band where temperatures might, just might, allow liquid water to pool on a rocky moon or a solid surface. It would be a world of eternal sunset, a landscape where the sun never rises or sets but hangs forever on the horizon, casting long, permanent shadows. The weather on such a world would be unlike anything we know. Imagine hurricane-force winds born from the extreme temperature difference, screaming from the hot side to the cold side in a never-ending torrent, trying and failing to balance the scales. This is not a planet that rotates, it is a planet that breathes one single tortured breath stretched across eternity. What strange, resilient forms of life could cling to existence in that fragile band of dusk? The violence of a tidal-locked world is one kind of cosmic pressure, but what about a planet that faces no pressure at all? We now encounter a class of worlds so bizarre they have earned the nickname puffy planets, gas giants that defy every expectation of density and structure. The first is WISP 107b, a world nearly the size of Jupiter but with less than 1/10 of its mass. To understand how strange this is, picture Jupiter as a dense, compact ball of swirling gas. Now take that same amount of material and inflate it like a balloon until it is 10 times larger. That is WISP 107b. Its density is so astonishingly low, it is less than that of a block of styrofoam. If you could find an ocean large enough, this planet would float. Its sibling in strangeness is HATP-1b, another Jupiter-sized world with only half of Jupiter's mass, giving it a similarly fluffy, inflated nature. These are not solid worlds, they are vast, tenuous atmospheres held together by the faintest whisper of gravity. The leading theory for their bizarre inflation points to an internal furnace. These planets orbit extremely close to their stars, and the intense stellar radiation pumps tremendous heat deep into their gaseous interiors. This heat acts like the burner under a hot air balloon, causing the entire atmosphere to expand outward against the pull of gravity. Another possibility is a delayed cooling process where internal heat from the planet's formation never properly escaped, keeping the gases perpetually puffed up. Or perhaps their atmospheres are rich in light elements that naturally resist compression. The result is a world with no clear surface, a hazy, distended sphere where the boundary between atmosphere and space is blurred beyond recognition. Standing on a theoretical platform in its upper layers, you would barely feel your own weight, gazing out into a sky that gradually deepens into a formless, glowing fog. These are planets without substance, cosmic ghosts that challenge our very definition of what a world can be. That tenuous, ghostly atmosphere is the very thing being violently torn away from another world. Meet HD 209458b, nicknamed Osiris, a planet that is quite literally evaporating before our eyes. This hot Jupiter orbits so close to its sun that its outer atmosphere is superheated to a staggering 10,000 degrees Celsius, causing it to balloon outward. The stellar radiation and fierce winds from the star do not just heat this gas, they blast it away into the void. The Hubble Space Telescope made the historic observation, detecting a giant cloud of hydrogen boiling off the planet and streaming behind it like the tail of a comet. This is not a gentle leak, it is a planetary hemorrhage. Osiris loses an estimated 10,000 tons of its atmosphere every single second, a vast, shimmering veil of gas being ripped into space. From a hypothetical vantage point, the planet would appear shrouded in a glowing, ethereal cocoon, with a brilliant tail stretching hundreds of thousands of miles into the darkness, pointing always away from the fury of its star. This discovery revealed a whole new class of planetary death, showing us that some worlds do not just form and endure, they actively disintegrate under the glare of their suns. The process tells astronomers about the extreme forces at play in these tight orbits and raises a haunting question: what remains when the atmosphere is completely stripped away? Is the final fate of Osiris a bare, scorched core, a skeletal world orbiting the corpse of its own vanished sky? The fate of a disintegrating world is a slow, silent unraveling, but the spectacle on WISP 76b is a cataclysm of biblical proportions. This is an ultra-hot Jupiter, a gas giant so close to its star that its year is less than 2 Earth days, and its dayside is a forge of almost incomprehensible heat. Temperatures there soar beyond 2,400 degrees Celsius, hotter than the surface of some red dwarf stars. At such extremes, the rules of chemistry are rewritten. Metals like iron do not melt, they vaporize, turning into a shimmering, gaseous fog that rises into the upper atmosphere. For years, this was just a terrifying theory, until the espresso instrument on the Very Large Telescope in Chile caught the spectral signature of iron vapor in the planet's dayside sky, the definitive proof of a world hot enough to boil metal. But the true anomaly, the moment that turned theory into a chilling reality, came when astronomers looked at the boundary between day and night. As the planet orbits, we see different phases, much like our moon. When they examined the twilight line, the terminator, the signature of iron vapor, vanished. It was simply not there on the cooler night side. The conclusion was as straightforward as it was staggering. The iron had not disappeared, it had fallen. Supersonic winds, born from the titanic temperature difference between the hemispheres, scream across the planet's surface. These 1,000-mile-per-hour gales sweep the vaporized iron from the dayside into the eternal darkness of the night side. There, in the profound cold that plunges hundreds of degrees, the iron vapor condenses. It forms droplets not of water but of molten metal, and then it rains. This is not a metaphor. On the night side of WASP-76b, it rains liquid iron. Picture standing on a hypothetical solid surface beneath that black, starless sky. The wind howls with the force of a continuous explosion. Then, through the gloom, a faint glow appears, growing brighter as incandescent droplets, each a tiny burning ember, begin to streak through the atmosphere. A downpour of molten metal falls, sizzling and hissing, painting the landscape in a hellish orange light. It is a world where the very sky is a chemical refinery, and the weather is a perpetual metallic storm. That metallic storm is a testament to the brutal physics of close orbits, a violence so intense it should leave no atmosphere behind at all. Yet against all odds, one world has not only survived this inferno, it has thrived. Meet LTT 9779b, an ultra-hot Neptune that by every rule of planetary science should not exist. This world is roughly the size of Neptune, with about 29 times the mass of Earth, and it orbits its star in a blistering 19-hour year. It is so close that its dayside temperature exceeds 1,700 degrees Celsius. This places it squarely in what astronomers call the hot Neptune desert, a region around stars where planets of Neptune's size and mass are almost never found. The reason is simple and destructive: stellar radiation. At such proximity, the fierce light and wind from a star should, over millions of years, rip away the thick, gaseous envelope of a Neptune-sized planet, leaving behind nothing but a barren, rocky core. We have seen this process begin with worlds like Osiris. For a planet as large as LTT 9779b to still have a substantial, puffy atmosphere in this zone is like finding a snowball resting comfortably in a blast furnace. It defies every model of planetary evolution. How has it clung to its sky? One compelling theory suggests it might be a fugitive, a planet that formed much farther out in its system and then migrated inward relatively recently. If this migration happened quickly on cosmic timescales, the planet may have arrived in the hot desert with its atmosphere still mostly intact, and we are witnessing it at the very beginning of its long, slow disintegration. Another possibility is that it possesses a uniquely massive core whose intense gravity acts as an anchor, holding onto the atmosphere against the stellar onslaught far more tenaciously than expected. Or perhaps its atmosphere is being actively replenished by volcanic outgassing from a geologically hyperactive interior. LTT 9779b is a glaring exception on the graph, a single defiant date, a point in an otherwise empty zone of destruction. Its very existence forces astronomers to reconsider the timelines of planetary migration and the complex battle between a star's fury and a world's will to hold itself together. While some worlds drown in metallic rain, others are cloaked in a shroud of exotic chemistry that sculpts their very climate. WASP-19b is a hot Jupiter with a truly alien sky, one laced with titanium oxide. On Earth, this compound is a rare curiosity, a component of some minerals and a brilliant white pigment in paints. But in the searing heat of this gas giant's upper atmosphere, titanium oxide transforms into something far more dramatic, a powerful heat trap. Astronomers detected its unique chemical signature using the Hubble Space Telescope, analyzing how the star's light filtered through the planet's gaseous envelope. The presence of this molecule solved a long-standing mystery about the planet's temperature profile. Normally, in an atmosphere like Earth's, temperature decreases as you go higher, which is why mountaintops are colder. But WASP-19b exhibits a thermal inversion, a layer where the temperature actually increases with altitude. This is its stratosphere, and it is hotter than the atmospheric layers beneath it. Titanium oxide is the architect of this inverted world. High in the atmosphere, this compound absorbs a tremendous amount of the incoming stellar radiation, much like a black shirt soaking up sunlight on a hot day. It heats up intensely, and that heat radiates, warming the entire layer around it. If you could visualize this atmosphere with a temperature color code, you would see a typical gradient of cooling colors, blues and greens, as you rose from the deep interior. But then, at a certain altitude, you would hit a startling band of red and orange, a hot layer blazing in the middle of the cooler sky before the colors faded again into the cold of outer space. This discovery was a landmark. It proved that exotic compounds we consider rare on our world can dominate and control the climate of another. Understanding this thermal inversion is crucial. It reveals the complex energy budget of an exoplanet, showing how absorbed heat is distributed, trapped, and irradiated. It means that to predict the conditions on a distant world, we must first decipher the intricate chemistry of its sky, a chemistry that can turn a simple molecule into a planetary-scale furnace. The chemistry of a sky can be a strange and powerful thing, but the very path a planet takes around its star can be stranger still. We now encounter worlds that do not follow the rules of the dance, moving in directions that defy the orderly formation of our own solar system. The first is WASP-17b, the same puffy planet we met earlier, but its atmosphere is not its only rebellion. This world possesses a retrograde orbit, meaning it circles its star in the opposite direction to the star's own spin. In our solar system, every planet orbits the Sun in the same direction the Sun rotates, like marbles spinning around the rim of a turning plate. WASP-17b is like a marble rolling backward against the spin of the plate. This single fact throws a wrench into the standard model of planetary formation. Planets are born from the same spinning disk of gas and dust that forms their star, so they should naturally inherit that same direction of motion. A retrograde orbit is a glaring sign of a violent past. Astronomers believe the most likely culprit is a gravitational catastrophe, a close encounter or even a collision with another massive object in the system's youth. This cosmic billiard shot could have flung the planet into a wildly tilted orbit, which then circularized over time into its current backward path. It is a permanent scar, a celestial record of a time when giants roamed the system and reshaped its architecture through sheer gravitational chaos. If a backward orbit is a record of chaos, then the path of Kepler 63b is a monument to it. This world takes strangeness to another level. It does not orbit around its star's equator at all. Instead, it travels in a polar orbit, passing almost directly over the star's north and south poles. Imagine if Earth's orbit took it looping over the Sun's poles. Our seasons and years would be unrecognizable. For a planet to achieve such a steeply inclined path, something truly dramatic must have happened. The leading theory points to a phenomenon called the Cos-I mechanism, a complex gravitational interaction. In a system with multiple planets, the gravitational tug of war between them can, over millions of years, slowly torque an orbit, pumping up its tilt while keeping its distance from the star roughly the same. It is a gradual, relentless process that can take a planet from a flat, orderly plane and stand it up on end. Alternatively, like its retrograde cousin, Kepler 63b could have been sent tumbling by a catastrophic scattering event, a gravitational kick from a passing giant that sent it careening onto its peculiar polar path. Together, these worlds with their backward and pole-to-pole orbits are more than just curiosities, they are forensic evidence. They tell us that the early lives of planetary systems are not the serene, orderly processes we once imagined. They are eras of gravitational turmoil where young planets jostle for position, scatter off one another, and are flung into orbits that seem to defy logic. These anomalous paths are the lasting signatures of that ancient violence frozen in time. They force us to ask if our own solar system had one more giant planet in its youth, could Earth have ended up orbiting over the Sun's poles or even backward? The calm order we see today may be the exception, not the rule, in a galaxy filled with the chaotic aftermath of planetary billiards. A world shaped by ancient chaos now gives way to one born from cosmic cooperation, a planet that should not even have a stable place to call home. In the constellation Cygnus, nearly 3,500 light-years away, orbits Kepler 47c. This gas giant is a marvel of celestial engineering, for it does not circle a single star but two. The Kepler 47 system is a tight binary, a pair of stars that pirouette around each other every 7.5 days. One is similar to our Sun, the other a dim, small red dwarf. In the gravitational whirlpool of such a duo, astronomers expected to find only disorder or perhaps no planets at all. The competing pulls of two suns should, in theory, make stable orbits nearly impossible, scattering any forming worlds into the void or sending them crashing into their stars. Yet there, tracing a graceful 203-day path, is Kepler 47c, a testament to an improbable balance. Its orbit is circumbinary, meaning it loops around both stars at once, a distant ringmaster overseeing a stellar dance. The very existence of this world forces a rewrite of the rules, proving that planets can form and persist in the most dynamically complex of nurseries. But the strangeness does not end with its address. Kepler 47c is another of those baffling puffy planets, a gas giant with a density so low it rivals that of cotton candy, despite orbiting within the system's habitable zone. This is the region where temperatures could allow liquid water to exist on a solid surface. Here we have a cosmic contradiction, a world that is both incredibly insubstantial and perfectly positioned for life, though not on itself. A gas giant has no solid surface, but it can have moons, and this is where the true wonder of Kepler 47c ignites the imagination. Picture yourself standing on a rocky, Earth-sized moon in orbit around this fluffy giant. Your sky is a perpetual spectacle. Two suns, one bright and yellow, the other a faint, deep red ember, wheel through the heavens in a complex, mesmerizing cycle. There would be double sunrises, double sunsets, and moments where the stars eclipse each other, casting strange, shifting shadows. The primary light would change in a rhythmic dance from the combined glare of both stars to the singular glow of one, then back again. And towering over all of it would be the magnificent banded visage of Kepler 47c itself, a striped colossus hanging in the sky, its gauzy atmosphere backlit by the twin suns. The conditions for life on such a moon are tantalizing. It would be warmed by the combined light of two stars and tidally heated by the gravitational flexing from the massive planet it orbits. This could create subsurface oceans, volcanic activity, and a stable climate. The discovery of Kepler 47c does more than add another world to the catalogue. It shatters our assumptions about where to look. It tells us that habitable real estate is not limited to planets orbiting single, sun-like stars. It can exist in the most unexpected of places, on a moon circling a cotton candy giant beneath the light of two suns, in a system that by all rights should be far too turbulent to allow such serenity to exist at all. The serene possibility of life under twin suns stands in stark contrast to a world actively unraveling in a stellar furnace. Among the most bizarre and morbidly fascinating discoveries is the star known as KIC 1255754 and the tiny, dying world that orbits it. This star, observed by the Kepler telescope, did something extraordinary. It flickered. Its light did not dip in the clean, periodic rhythm of a planet transiting, but in a wild, erratic, and unpredictable pattern. The dimming varied dramatically from one orbit to the next, sometimes blocking a full 1% of the starlight, other times barely registering at all. It was as if something was passing in front of the star, but that something was changing shape and size constantly. The only explanation that fit this chaotic data was as terrifying as it was elegant, a planet in its final death throes. Designated KIC 1255754 this is a small, rocky world, perhaps even smaller than Mercury, locked in an orbit so tight its year lasts a mere 15 hours. The dayside temperature is estimated at over 2,000 degrees Celsius, hot enough to vaporize rock. The surface does not just melt, it boils. Silicate minerals and metals are superheated into a vapor that rises in great plumes from the planetary surface. This vapor then cools as it expands into space, condensing into a fine cloud of dust and tiny debris particles. The planet is essentially creating its own funeral shroud. This immense comet-like tail of dust streams behind the planet, blown by the intense radiation pressure from the star, but the process is not steady. The vaporization rate likely depends on volatile materials on the surface, geological activity like volcanoes, or the planet's own uneven topography. Some orbits the planet might belch forth a colossal, opaque cloud that casts a deep shadow. Other orbits, the outgassing might be a faint wisp causing only a slight dimming. From our distant vantage point, we are not watching a solid world transit. We are witnessing the chaotic, dusty exhalations of a world being boiled alive. The detection method itself was a triumph of pattern recognition amidst noise. Astronomers had to sift through the Kepler data, looking for stars that did not behave in the standard, predictable way. They had to develop models of dusty clouds of varying density and size to see what kind of shadow they would cast. It was like trying to identify a person not by their silhouette, but by the shifting, shimmering pattern of smoke rising from them. This phenomenon gives us a front-row seat to planetary destruction on a human timescale. Over thousands or millions of years, this relentless erosion will completely strip the planet of its mass, leaving behind perhaps only a tiny, dense core, a burnt cinder orbiting its star. KIC 1255754 is a stark reminder that some worlds are not permanent. They are transient events, and we are fortunate enough to catch one in the fleeting, dusty act of its own disappearance. That dusty, evaporating world is a lesson in cosmic impermanence, but some planets seem to defy gravity itself with their impossible lightness. In the Kepler 51 system, we find not one, but three worlds that challenge our understanding of what a planet can be. They are the ultimate super puffs, with densities so low they make the earlier puffy planets seem almost dense by comparison. The trio, Kepler 51b, C, and D, are all roughly the size of Jupiter or larger, yet their masses are only a few times that of Earth. To put that in perspective, if Saturn were a fluffy pillow, these worlds would be a cloud of cotton candy. Their average density is less than 1/10 of a gram per cubic centimeter, which is about the density of a dry marshmallow. If you could find an ocean large enough, these planets would not just float, they would bob on the surface like giant, ethereal bath toys. The secret to their incredible puffiness lies in their atmospheres. Unlike Jupiter, which has a massive, dense core beneath its thick layers of gas, these superpuffs appear to be almost all atmosphere. Their extended shrouds of hydrogen and helium are not a thin skin over a solid world. They are the world itself, making up a staggering fraction of the planet's total radius. Imagine a planet where, if you tried to descend, you would simply pass through increasingly dense fog for thousands of miles, with no discernible surface ever appearing beneath you. The formation of such objects is a profound puzzle. How did they gather such enormous, bloated envelopes of light gas without also accumulating the solid material to build a substantial core? One theory suggests they formed much farther from their star, in the cold outer reaches of the protoplanetary disk where ices and gases were plentiful. They may have then migrated inward to their current orbits, arriving with their fluffy coats intact. Another, more tantalizing idea is that we are catching them at a very special and fleeting moment in their cosmic lives. Their extended atmospheres may be temporary, inflated by intense internal heat left over from their formation or by the relentless irradiation from their young star. This heat acts like a constant internal updraft, holding the atmosphere in a distended, puffy state against the pull of gravity. This leads to a fascinating prediction about their future. As these planets continue to age and cool over hundreds of millions of years, that internal heat will slowly dissipate. Without that energy to support it, the enormous atmosphere will begin to contract. The relentless stellar wind may also begin to strip away the outermost layers, eroding the fluff. Astronomers theorize that what we see today as a marshmallow world may, in the distant future, transform into something more familiar, a denser mini-Neptune with a more compact gas envelope, or even a bare super-Earth core if the atmosphere is stripped away entirely. The Kepler-51 system, then, is not just a gallery of oddities. It could be a time capsule showing us different stages of planetary evolution. We might be witnessing a phase that is normally brief and rarely seen, the exuberant, bloated adolescence of a world before it settles into a more mature and compact form. What other fleeting stages of a planet's life cycle are we missing because they pass in just a cosmic blink? If the worlds we have seen so far seem like visions from a fever dream, the reality of WASP 121b is something far more opulent and terrifying. This is an ultra-hot Jupiter that takes the concept of extreme weather and transforms it into a spectacle of pure, vaporized geology. Orbiting so close to its star that a full year passes in just 30 hours, its day side is a crucible reaching a staggering 2,500 degrees Celsius. At such temperatures, the very rocks cease to be solid. Common terrestrial minerals, the stuff of our mountains and beaches, do not merely melt here, they boil. They are ripped apart at the molecular level and enter the atmosphere not as dust but as a shimmering metallic vapor. Astronomers using the Hubble Space Telescope performed a kind of cosmic alchemy, dissecting the starlight that filtered through the planet's outer layers. Within that spectral signature, they found the unmistakable fingerprints of vaporized metals, gaseous iron and magnesium, and even the exotic element vanadium. This was not a thin trace, it was a substantial component of the upper atmosphere. The heat is so intense that these heavy elements are lifted high into the sky, far above where they would normally condense and fall. But the atmosphere of WASP 121b has even more secrets. The data strongly suggests the presence of something even more extraordinary, clouds not of water but of vaporized rock. The leading hypothesis paints a picture of a sky in perpetual, glittering upheaval. Silicate minerals, the primary component of sand and rock, are vaporized on the scorching day side. These silicate vapors are then carried aloft by supersonic winds. As they reach the cooler, higher altitudes of the upper atmosphere, they begin to condense. But they do not form raindrops. Instead, they crystallize into microscopic particles of molten rock or corundum, the mineral that forms rubies and sapphires. Imagine, then, standing on a hypothetical platform within this world's immense gravity well. you are enveloped in a haze that glows with the reflected light of the nearby star. The sky is not blue, but a shimmering, incandescent orange streaked with bands of darker vapor, and within that sky, clouds of what is essentially hot sand, or perhaps even droplets of molten gemstone, drift and swirl. Storms on this world would not unleash water, but a mist of incandescent silica and a rain of liquid sapphire. This is a planet where the boundary between atmosphere and lithosphere has utterly dissolved. The ground, if one could even call it that, is an ocean of vaporized stone, and the sky is a glittering, mineral-laden furnace. It redefines the very meaning of a storm cloud, presenting us with a world so extreme that its weather is forged from the bones of planets themselves. What other breathtaking, impossible forms of precipitation might be falling on worlds we have yet to discover? Drifting through the cold, starless void between suns, a solitary world glows with its own inner light. This is PSOJ 318.5-22, an orphan planet untethered from any star, a true cosmic rogue. Discovered in the Pan-STARRS survey, this object is not a failed star, but a genuine gas giant, roughly 6 times the mass of Jupiter, yet it wanders the galaxy alone. Its very existence is a profound anomaly. Planets, by our traditional definition, form in disks around young stars, and they are expected to remain bound to that star by gravity. PSOJ 318.5-22, however, was somehow ejected from its birthplace in a violent gravitational encounter, cast adrift to wander the interstellar darkness forever. The deeper mystery, however, is not just that we found it, but how we found it. This world is not transiting a star, nor is it reflecting any starlight. It is visible to us for one haunting reason: its atmosphere is still glowing. This faint, persistent luminescence comes from the residual heat trapped deep within the planet, leftover energy from the violent process of its formation over 20 million years ago. It is the cooling ember of a world born in chaos, now sailing through an eternal, silent night. For astronomers, detecting and analyzing the light from this lone wanderer's atmosphere is a landmark achievement. It allows them to study the atmospheric composition of a gas giant in pristine isolation, free from the overwhelming glare and complicating effects of a parent star. They can measure the chemicals present, the cloud structures, and the thermal profile of a world shaped solely by its own internal dynamics and the chill of space. This turns the rogue planet into a unique laboratory. The implications stretch far beyond atmospheric science. In the absolute cold of interstellar space, with no external source of warmth, any possibility for active chemistry or even life seems to vanish. Yet, these orphan worlds are not necessarily frozen dead. A massive gas giant like this one, or even a smaller, rocky rogue, could retain a molten core for billions of years, heated by radioactive decay and gravitational contraction. That internal furnace could, in theory, power volcanic activity on a rocky moon or a subsurface ocean beneath a global ice shell, much like Jupiter's moon Europa. In the perpetual darkness, such a hidden ocean, warmed from within, could be a sanctuary for exotic, chemosynthetic life forms that never see a sunrise. Furthermore, the faint glow of the atmosphere itself suggests complex thermal processes at work. Could atmospheric circulation driven by internal heat create dynamic weather patterns even without a sun? Could chemical reactions sparked by internal warmth and cosmic radiation create probiotic molecules in those alien skies? PSOJ 318.5-22 is more than a lonely curiosity, it is a key. It unlocks a new chapter in planetary science, forcing us to consider that habitable conditions are not exclusive to the Goldilocks zones around stars. Life, in its most resilient and strange forms, might also find a way in the sunless abyss, warmed from within by the dying heart of a world that has no sun. While some worlds glow with the heat of their own formation, others cling to a sky that should have been stripped away long ago. GJ1132b is a rocky planet nearly identical in size to Earth, orbiting a small, dim red dwarf star just 39 light-years away. It is a world of scorching proximity, completing an orbit in a mere 1.6 Earth days, so close that its surface temperature likely exceeds 200 degrees Celsius. For years, astronomers assumed any atmosphere around such a planet would be quickly blasted away by the relentless radiation of its star, leaving behind a barren, airless rock. But when they pointed the Hubble Space Telescope at this system, they saw something impossible: the subtle fingerprint of an atmosphere. The starlight dimmed in a specific way as the planet passed in front of its sun, revealing a thin but detectable shroud of gases. The discovery was monumental. It marked the first time an atmosphere had been detected around a terrestrial world outside our solar system. The immediate question was, how could it possibly still be there? The answer points to a world not of serene landscapes, but of unending geological fury. The leading theory suggests this is not a primordial atmosphere, one left over from the planet's birth. That ancient sky would have evaporated eons ago. Instead, GJ1132b is likely sporting a secondary atmosphere, one that is being actively manufactured and replenished from within. The planet is probably tidally locked, with one hemisphere forever facing its star. This creates immense internal stress as the gravitational pull from the star constantly kneads the planet's interior. This process, tidal heating, combined with heat from radioactive decay, could keep the mantle partially molten, fueling planet-wide volcanic activity on a scale that makes Earth's most explosive eruptions seem tame. Picture this world from orbit. You would not see blue oceans or green continents. Instead, the surface might be a global panorama of black, cooled lava flows, cracked and wrinkled like the skin of a dried fruit. Countless volcanic vents and fissures would dot the landscape, glowing with a fierce orange-red light against the perpetual twilight of the dayside. Great plumes of gas and ash would rise continuously, pumping new material into the sky. This outgassing is the planet's lifeline. Volcanoes belch forth a mixture of gases, primarily hydrogen, methane, and hydrogen cyanide, along with sulfur compounds. These gases form a thin, hazy envelope that constantly leaks into space under the stellar assault, only to be replaced by fresh eruptions from below. It is a dynamic equilibrium, a planetary breathing cycle where the world exhales its atmosphere into the void and then draws a new breath from its molten heart. The sky on GJ1132b would be a perpetual, sickly yellow-brown, thick with photochemical smog created as stellar radiation breaks apart the volcanic gases. The air might smell of rotten eggs from hydrogen sulfide, and the faint light from the red dwarf star would struggle to penetrate the gloom, casting the volcanic plains in a dim, hellish twilight. This discovery transforms our understanding of terrestrial exoplanets. It proves that atmospheres can persist in the most hostile environments, not as fragile relics, but as active, living systems sustained by the world's own internal furnace. It suggests that geology is not just a planetary feature, it can be a planetary survival strategy. If a world like this can maintain an atmosphere through sheer volcanic willpower, then perhaps other seemingly inhospitable planets, bathed in radiation or locked in frozen orbits, might also harbor hidden, geologically powered skies where unexpected chemistry and just maybe the precursors to something more could take hold. The volcanic breath of a world clinging to its sky is a testament to cosmic resilience, but some planets are born into a gravitational maze from which there is no simple escape. Far beyond any single star in the constellation Cygnus lies the system known as KOI-5, home to a world called KOI-5b. This is not a planet with one sun or even two but three. It is a real world that mirrors the fictional vistas of Tatooine, but with a celestial dance far more complex. The system is a hierarchical triple, a delicate gravitational arrangement where two stars, KOI5A and B, orbit each other in a tight 30-day embrace. Around the primary star, KOI5A, the planet itself orbits, but this entire pair, star and planet, is then slowly circled by a third star, KOI5C, over a vast distance that takes nearly 1,000 years to complete one full loop. The planet's very existence in this three-body chaos is the first great puzzle. For a world to form, it needs a stable, peaceful disk of gas and dust around its star. The gravitational tugs from two other nearby suns should have ripped such a disk apart, scattering the planet building material or preventing it from coalescing in the first place. That KOI5AB formed at all suggests it either assembled quickly before the stellar turbulence could destroy its cradle, or it migrated inward from a more stable region farther out, surviving a perilous journey through a gravitational gauntlet. The planet itself is a gas giant, roughly half the mass of Saturn, but its true nature is defined by its address. From the perspective of this world, the sky is a theater of perpetual shifting light. For roughly half of its orbit, the planet's primary sun, KOI5A, dominates the heavens, but as the planet moves, the second star of the close binary pair, KOI5B, rises. It appears not as a distant point, but as an intensely bright companion, hundreds of times more luminous in the sky than our full moon. There would be periods of double daylight where both close suns are above the horizon, casting stark, overlapping shadows. Then, as the stars continue their own orbital dance, one would set, leaving the other to rule the sky alone, and this entire cycle repeats every 5 Earth days, the length of the planet's year. But the spectacle does not end there. Hanging in the distance, a constant fixture in the day or night sky, is the third sun, KOI5C. It would shine with the steady, cold brightness of a brilliant star, a reminder of the wider gravitational clockwork governing this system. The daylight patterns would be endlessly variable, with sunrises and sunsets involving one, two, or even a primary sun with the distant third always visible. The concept of seasons would be untethered from a simple orbit, instead tied to the complex interplay of all three stellar bodies. The gravitational forces at play would also create a world of profound and unpredictable tides, flexing its atmosphere and potentially heating its interior. KOI5AB is a lesson in celestial mechanics written in light and gravity, proving that planets can find a precarious balance even in the most crowded and dynamic of stellar neighborhoods. If life could exist on a moon here, its very sense of time would be built upon a rhythm of three suns. The gravitational tides that shape a triple star system are a gentle dance compared to the violent, predatory pull tearing another world apart. WASP-12b is a hot Jupiter caught in a death spiral, a planet being actively consumed by its own sun. This world takes the concept of a close orbit into the realm of the catastrophic. It circles its star in a mere 26 hours, so close that the star's gravity does not just heat the planet, it physically stretches it. The immense tidal forces have distorted WASP-12b from a sphere into an egg shape, an oblate spheroid pulled toward the star like taffy. But the star's appetite does not stop at distortion. The same gravitational force that creates the tides is also pulling material directly off the planet's puffed-up atmosphere. Think of it as a cosmic siphon. The star's gravity is stronger on the side of the planet facing it, creating a point where material can overcome the planet's own gravitational hold and flow directly onto the stellar surface. This isn't a slow leak, it's a planetary hemorrhage on a scale that defies belief. The planet is losing an estimated 6 billion metric tons of mass every second. At that rate, astronomers estimate it could be completely destroyed within the next 10 million years, a blink in cosmic time. The evidence for this ongoing destruction is written in the starlight itself. When a normal, spherical planet transits its star, it creates a symmetrical dip in brightness, a clean, U-shaped curve as it moves fully in front and then fully away. WASP-12b's transit curve is lopsided, skewed. The dip begins normally as the planet's leading edge first touches the star's disk, but the trailing edge of the dip is drawn out, shallower and messy. This asymmetry is the smoking gun. It is caused by a vast, diffuse cloud of material that has been stripped from the planet, a comet-like tail of hot gas that trails behind it in its orbit. This tail is partially transparent, so it doesn't block all the starlight at once, creating that drawn-out, smeared exit from the transit. Observations with the Hubble Space Telescope confirmed this by detecting the spectral signature of various metals, like magnesium, not just on the planet itself, but in this extended stream of lost atmosphere flowing toward the star. From a hypothetical vantage point, the scene would be one of terrifying beauty. The planet itself would glow a fierce, angry red, its atmosphere boiling and churning as it streams away in a brilliant, incandescent arc, a bridge of fire stretching from the dying world directly into the heart of its devourer. The star, for its part, is not a passive participant. It is actively feeding, accreting this stolen material onto its surface, which may subtly alter its own chemistry and behavior. WASP-12b is more than an anomaly, it is a snapshot of planetary extinction. We are witnessing the final act for a world that ventured too close to its sun, a stark reminder that even giants are not immune to the ultimate power of gravity. What does the star gain from this feast, and what signature does a stellar meal leave behind? The relentless stellar furnace that consumes a world is matched only by the forge-like heat radiating from another. KELT-9b holds the grim title of the hottest exoplanet ever discovered, a scorching giant where the dayside temperature soars to nearly 4,300 degrees Celsius. That is hotter than the surface of many red dwarf stars. At such extremes, molecules cannot hold together. Even sturdy hydrogen gas is ripped apart into its constituent atoms. This world is not just hot, it is being chemically disassembled by the sheer fury of its sun. Yet within this inferno lies a subtle and puzzling anomaly, a clue written in infrared light. When astronomers measured the heat radiating from the planet's night side, the hemisphere locked in permanent shadow, they expected to find profound cold. After all, with no direct source of stellar energy, the night side should be a deep freeze by comparison. Instead, they detected a significant and unexplained infrared glow. The night side is still blisteringly hot with temperatures around 2,000 degrees Celsius. The mystery is not that it is hot, but why it is so hot. How does such immense heat cross from the blazing dayside to the eternal night? The distance is vast and the planet is tidally locked, so the heat cannot simply be carried by a slow rotation. The answer appears to lie in a previously unseen atmospheric superhighway. On a normal planet, heat is transported by winds and ocean currents. On KELT-9b, the mechanism is far more violent and efficient. The leading theory involves the very destruction of the atmosphere's main component. On the day side, the intense stellar radiation tears molecular hydrogen apart, a process called thermal dissociation. This requires a colossal amount of energy which is absorbed by the gas. Then, these individual hydrogen atoms are swept by supersonic winds across the terminator to the night side. In the relative cool of the shadowed hemisphere, the atoms find each other again and recombine back into hydrogen molecules. This act of recombination releases all that stored energy as a burst of heat, flooding the night side with warmth. It is a planetary-scale heat engine using the atmosphere itself as a working fluid. The hydrogen atoms act like countless tiny batteries, charging with stellar energy on the day side, traveling across the twilight line, and then discharging that energy as heat on the night side. This continuous cycle of destruction and rebirth may be what keeps the shadowed hemisphere glowing like a banked coal. It suggests atmospheric dynamics of staggering efficiency, a global circulatory system that defies our Earth-bound intuition about weather and climate. If this process is real, it paints a picture of a world where the sky is not just moving air, but a shimmering, reactive plasma, constantly cycling between atomic and molecular states in a desperate attempt to balance an impossible thermal load. What other exotic forms of energy transfer are at work on worlds that push the very limits of physical law? That relentless heat engine of destruction offers a stark contrast to a world where the atmosphere is not a chaotic plasma, but a surprisingly clear and revealing window. HATP 11b is a Neptune-sized world, but it is nothing like the cloudy, banded giant in our own solar system. This exoplanet, orbiting a star about 120 light-years away, presented astronomers with a gift, an atmosphere almost completely free of clouds. The discovery came when the Hubble and Spitzer space telescopes observed the planet as it passed in front of its star. By analyzing the precise way the starlight dimmed at different wavelengths, scientists could detect the chemical fingerprints of specific gases in the planet's upper atmosphere. What they found was the unambiguous signature of water vapor. This in itself was not entirely unexpected, but the clarity of the signal was. On many other cool gas giants, thick clouds of silicate or salt crystals high in the atmosphere act like a blanket, obscuring our view of the deeper layers and muddling the chemical signatures. HATP 11b had no such blanket. Its sky was remarkably transparent, allowing telescopes to peer deep into its atmospheric structure and confirm the presence of water vapor with exceptional certainty. This clear atmosphere transforms the planet into a natural cosmic thermometer. Here is how it works. Water vapor absorbs specific wavelengths of infrared light, the kind of heat radiation the planet emits. By measuring exactly how much infrared light is being absorbed at different wavelengths, astronomers can determine the temperature of the atmospheric layer where that absorption is happening. Deeper, hotter layers emit more radiation at certain wavelengths, while cooler, higher layers emit less. The water vapor acts as a marker, a chemical dipstick that allows scientists to take the temperature at various altitudes. It is like having a network of weather balloons distributed throughout the planet's sky, each one reporting back a data point on the thermal profile. This clean measurement is invaluable because it provides a baseline, a clear picture of how heat is distributed in an atmosphere uncomplicated by obscuring clouds. The very existence of this cloud-free Neptune is a profound puzzle. Our understanding of planetary atmospheres suggested that worlds of this size and temperature, often called cool Neptunes, should be shrouded in cloud. As atmospheric gases cool with altitude, various compounds should condense out to form cloud decks, much like water vapor forms clouds on Earth. For HATP 11b to be so clear implies something unusual is at work in its atmospheric chemistry or circulation. Perhaps powerful vertical winds are constantly mixing the gases, preventing them from cooling and condensing at the expected altitudes. Maybe its atmosphere is chemically dry, in a way that inhibits the formation of the typical cloud seed particles. Or it could be that we are catching this planet in a unique, transient clear phase. Whatever the reason, this anomaly provides a rare and pristine laboratory. It gives astronomers a cleaner signal, a less corrupted view into the atmospheric composition and dynamics of a world very different from our own. By studying this clear sky, we can build better models of how these common planetary atmospheres work, models that must now account for the possibility of unexpected clarity. In a field where data is often faint and fuzzy, HATP 11b stands out as a sharp, detailed portrait, a world that chose to reveal its secrets rather than hide them behind a veil. This crystal clarity offers a pristine view of atmospheric physics, but some planetary systems achieve a different kind of perfection, one of breathtaking orbital harmony. Far from the chaotic tug-of-war of triple stars, there exists a pocket of the cosmos where worlds move in a rhythm so precise it resembles a celestial symphony. This is the TRAPPIST-1 system, a family of 7 rocky planets all roughly the size of Earth, orbiting a cool, dim red dwarf star 39 light-years away. While the discovery of so many Earth-sized worlds in one place captured global attention, the deeper, more profound anomaly lies not in their size but in their motion. These seven sisters are locked in an intricate chain of orbital resonances, a gravitational dance of such delicate precision it defies simple explanation. An orbital resonance is a kind of gravitational synchronization. When two orbiting bodies exert a regular, periodic tug on each other, their orbital periods can settle into a stable ratio of whole numbers. In our own solar system, we see a simple example with Jupiter's moons Io, Europa, and Ganymede. For every 4 orbits Io makes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1, a 4-to-2-to-1 resonance. The TRAPPIST-1 system takes this concept to an astonishing level of complexity. Its 7 planets are all linked together in a grand, interconnected chain. The orbital periods are not random, they exist in near-perfect ratios. For example, when the innermost planet completes 8 orbits, the second planet completes exactly 5. When that second planet completes 5 orbits, the third completes 3. This pattern continues outward through the entire system, with pairs of planets locked in resonant ratios like 5-to-3, 3-to-2, and 4-to-3. This is not a coincidence. Such a finely tuned system almost certainly formed through a process of gentle, inward migration. The leading theory suggests these planets assembled farther out from their star in the cooler regions of the protoplanetary disk. As they formed, their gravitational interactions with the disk of gas and dust caused them to slowly spiral inward toward the star, but they did not fall chaotically. Instead, they caught each other gravitationally, like gears engaging. As one planet migrated, its gravity would tug on the next planet out, pulling it into a resonant lock. That planet would then tug on the next, and so on, until all 7 were linked in this elegant, descending chain. This peaceful migration is what gives the system its remarkable long-term stability. The resonant tugs are predictable and gentle, keeping the orbits orderly and preventing the planets from crashing into each other over billions of years. It is a self-correcting mechanism. If one planet starts to drift slightly out of rhythm, the gravitational nudges from its resonant partners gently push it back into line. Yet, this very perfection is the source of a deep puzzle. How did such an intricate clockwork system assemble itself around a tiny, turbulent red dwarf star? Red dwarfs are notorious for their violent youth, erupting with frequent and powerful stellar flares that could easily disrupt fragile planetary disks. The fact that this delicate resonant chain survived that early tempest suggests the planets either formed remarkably quickly before the worst of the stellar tantrums, or that their mutual gravitational bonds are incredibly resilient. Furthermore, the complexity of a 7-world resonance chain pushes our models of planetary migration to their limits. It requires a disk of just the right density and lifespan, and a migration process that was slow, smooth, and coherent across all 7 worlds. It is a testament to a formation history of exceptional calm and coordination in a universe often defined by chaos. To stand on one of these worlds would be to experience time marked by this cosmic clockwork. The other planets would not wander randomly through the sky. They would appear and reappear in predictable, rhythmic patterns, their positions dictated by the silent mathematics of gravity. This resonant chain is more than an orbital curiosity. It is a fossil record of the system's birth, a preserved moment of planetary migration frozen in time, challenging us to understand how such fragile harmony could emerge from the primordial storm. The delicate clockwork of the TRAPPIST-1 system reveals a universe capable of profound order, but the search for other worlds often uncovers signals so faint and complex they border on the edge of perception. This brings us to Kepler 1625b, a gas giant thousands of light years away, and the tantalizing, controversial whisper of a companion. the data from the Kepler Space Telescope showed something extraordinary about this planet's transit, the regular dip in starlight as it passed in front of its sun. The main dip was clear, but when scientists at Columbia University, led by Alex Tichy and David Kipping, scrutinized the light curve with exquisite care, they noticed two additional anomalies. First, there was a smaller, secondary dip in brightness that occurred after the planet had finished its main transit. This faint dimming appeared consistently, trailing the planet like a shadow. Second, the planet itself began its transit 75 minutes earlier than predicted, as if something massive was tugging it gravitationally, altering its precise timing. The most compelling explanation for both these clues was not another planet but a moon, and not just any moon, a colossal one, potentially the size of Neptune, orbiting this distant gas giant. If confirmed, this object, dubbed Kepler 1625b, would be the first exomoon ever detected, a discovery of staggering importance. The evidence, however, ignited a firestorm of scientific debate. The signals were at the very limit of what the Kepler telescope could detect, buried in astronomical noise. Critics argued the secondary dip could be caused by stellar activity, a sunspot on the star itself rotating into view. The timing variation of the planet could potentially be explained by the gravitational pull of another, unseen planet in the system rather than a moon. The follow-up observations with the Hubble Space Telescope added more data but not definitive proof, showing hints of the secondary dip but with less clarity than hoped. This is the razor's edge of modern astronomy, where a monumental discovery is balanced against the rigorous burden of proof. Confirming an exomoon is exponentially harder than confirming a planet. A moon's signal is a tiny distortion within the already tiny signal of its host planet. It requires multiple, pristine transits observed with the most powerful telescopes, and even then, alternative explanations must be painstakingly ruled out. The case for Kepler 1625b remains open, a promising candidate suspended in a state of tantalizing uncertainty. Yet, the mere possibility cracks open a new frontier. Our own solar system is rich with moons, worlds like Europa and Enceladus that harbor subsurface oceans and are prime targets in the search for life. If a gas giant in a distant system can host a moon the size of a planet, then moons are not mere accessories. They could be dominant features of the galactic landscape. The implications for habitability are profound. A moon orbiting a gas giant within its star's habitable zone would experience a complex environment. It would receive light and heat from its sun, but also significant tidal heating from the gravitational flexing caused by its giant planet host. This dual energy source could maintain liquid water and geologic activity for billions of years, potentially creating stable, life-friendly environments even on moons that would be frozen ice balls if they orbited a star alone. The quest for Kepler 1625b, then, is about more than one moon. It is a test of our ability to see the smallest details in the farthest lights and a step toward answering a foundational question. In a galaxy filled with planets, how many are accompanied by hidden, watery worlds, not as the primary act, but as supporting characters in their own epic tales of survival? That search for faint, hidden companions leads us to a world that is itself a master of hiding, a planet that consumes light. Meet TRES-2b, the darkest exoplanet ever discovered, a gas giant that reflects less than 1% of the starlight that falls upon it. This world is blacker than coal, blacker than a pool of ink, blacker even than a freshly paved road on a moonless night. Its surface, or rather the upper reaches of its atmosphere, is the most light-absorbent natural surface known in the universe. This profound darkness, this almost complete lack of reflectivity, is what astronomers call an extremely low albedo. For comparison, our own moon, which looks so bright in our night sky, reflects about 12% of the sun's light. Jupiter, a similarly sized gas giant, reflects over 50% thanks to its bright, reflective clouds of ammonia. TRES-2b is an abyss. It absorbs 99.9% of the photons that strike it, transforming that radiant energy into a searing, internal heat that must churn its atmosphere into a violent frenzy. The central mystery is, what is its sky made of? What exotic cocktail of chemicals creates a shroud of such perfect blackness? The leading suspects are elements that are excellent at absorbing visible light. The planet's scorching temperature, around 980 degrees Celsius, is hot enough to vaporize metals like sodium and potassium. These gaseous metals, floating high in the atmosphere, could be acting like a cosmic black paint, soaking up photons across the spectrum. Another candidate is titanium oxide, the same compound that creates a thermal inversion on other worlds. But here, in a different atmospheric configuration and temperature, it might exist not as a reflective cloud, but as a pervasive, light-hungry vapor. It is also possible the atmosphere is simply devoid of the reflective cloud decks we see on Jupiter. Instead of bright white ammonia, the clouds here could be composed of dark compounds like vaporized rock or sooty carbon compounds, further deepening the gloom. Now picture the view from within this perpetual twilight. You are not standing on a surface, for there is none, but floating in the deep atmosphere of a gas giant. Above you, the sky is not a blue dome or a starry night. It is an utter and complete void, an infinite blackness. No clouds gleam, no atmospheric haze scatters light. It is a black so deep it feels like a physical presence, and yet there is one source of illumination, one glaring exception to the dark. Hanging in that black sky is the planet's host star, glowing with a dim, deep red light. Because the atmosphere absorbs almost all light, there is no diffusion, no softening of the star's image. It would appear as a sharp, piercing pinprick of crimson fire, a brilliant, unblinking red eye suspended in the nothingness. You would see no corona, no atmospheric halo, just a stark, singular point of light against an absolute black backdrop. The star would cast harsh, razor-sharp shadows, but those shadows would fade into the overwhelming dark just a few feet away. There would be no sunset, no dawn, only that eternal, glaring red eye in an endless black sky. This world challenges our very notion of what a sky can be. It is not a canvas for color and light, but a void that devours it, a reminder that the palette of the cosmos includes shades far darker than we ever dreamed. That profound darkness is a constant, but for one world, even the path it walks is never the same. Kepler 413b is a planet of profound celestial instability, a world whose very orbit wobbles with such violence that it disappears from our view for a decade at a time. This gas giant, roughly the size of Neptune, lives in a binary star system, circling a pair of stars, one orange and one red dwarf, that orbit each other every 10 days. The planet's path is circumbinary, looping around both stars in a 330-day year. But this is no flat, stable ring like Saturn's. Instead, the planet's entire orbital plane is in a state of constant, rapid gyration, a phenomenon called precession. Imagine a spinning top just as it begins to wobble, its axis tracing a slow circle in the air. Now, picture that wobble happening at an astonishing speed. The gravitational tug-of-war between the two closely orbiting stars constantly torques the planet's orbit, causing its plane to tilt back and forth with a cycle of just 11 years. From our distant vantage point on Earth, this creates a bizarre observational reality. For about 2.5 years, the planet's orbit is aligned just right so that it passes directly between its stars and us, causing a regular, detectable transit. Then, for the next 8 years, the precession tilts the orbit out of alignment. The planet no longer crosses the faces of its stars from our perspective. It passes above or below them, vanishing from our detection entirely. It enters a 10-year observational hiatus, a cosmic game of hide and seek dictated by the relentless physics of a three-body dance. This extreme precession would make the concept of a stable climate utterly alien. If this world possessed a solid surface or large moons, their seasons would be driven not by a gentle axial tilt, but by the violent wobbling of the entire orbital plane relative to the binary stars. The angle at which starlight strikes the planet would change dramatically over a single human decade. One era might see a hemisphere bathed in constant, direct light from both suns, a scorching double summer. A few years later, that same hemisphere could be tilted into a deep, oblique twilight, a long winter where the suns hang low on the horizon or even dip below it for extended periods, depending on the moon's own rotation. The patterns of daylight, the intensity of radiation, and the temperature extremes would shift in a chaotic, unpredictable rhythm far more complex than any simple seasonal cycle. The gravitational forces flexing the planet would also generate immense tidal heating within its interior or on any orbiting moons, potentially fueling global volcanism or subsurface oceans. Life, if it could take hold in such a mercurial environment, would need to be incredibly resilient, adapting to a world where the very rules of sunshine and darkness are rewritten every few years. Kepler 413b is a lesson in celestial impermanence, a world whose fundamental relationship with its suns is never settled, forever dancing on the edge of our vision and understanding. The sky of a wobbling world is a lesson in celestial chaos, but our final anomaly presents a structure of such scale and precision it seems carved by the gods themselves. This is not a planet as we know it, but an object known as J1407b, a possible brown dwarf or rogue planet, encircled by a ring system of almost incomprehensible grandeur. While Saturn's magnificent rings span about 280,000 kilometers at their widest, the rings around J1407b are over 200 times larger, stretching nearly 120 million kilometers across. If this colossal ring system were placed in our own solar system, it would stretch from the Sun to well past the orbit of Venus, utterly dwarfing the planets. We did not see these rings directly, but inferred their existence from one of the most bizarre stellar eclipses ever recorded. The parent star, J1407, underwent a complex series of dimming events lasting 56 days, where its light did not just dip smoothly, but flickered and plunged in a wild, unpredictable pattern. This was not a clean, planetary transit, but the silhouette of an entire cosmic construction site passing in front of the star, a vast, intricate disk of dust and debris with complex structures blocking the light in a constantly shifting mosaic. The detailed light curve revealed not just a single shadow, but a sequence of deep, sharp dips within the broader eclipse. These were the telltale signatures of gaps within the rings, clean lanes swept clear by the gravitational influence of embedded bodies. Just as Saturn's shepherd moons like Pan and Daphne's carve and maintain the sharp edges of the planet's rings, these gaps in J1407b's disk strongly suggest the presence of exomoons, perhaps dozens of them, each clearing its own path through the primordial material. Some of these gaps are enormous, hinting at moons that could themselves be the size of Mars or even Earth, acting as celestial gardeners on a staggering scale. The true nature of the central object remains one of astronomy's great puzzles. Is it a very young, giant gas planet, a failed star known as a brown dwarf, or even an orphaned world drifting through space with its entire satellite system still intact? Its mass is estimated to be between 20 and 40 times that of Jupiter, placing it right on the fuzzy boundary between planet and brown dwarf. This ambiguity makes J1407b a unique and precious laboratory. It is a snapshot of a system in the act of moon formation, a scaled-up version of what our own solar system may have looked like in its infancy, when the Sun was surrounded by a vast protoplanetary disk from which the planets and their moons coalesced. By studying the complex patterns in the starlight, astronomers can reverse engineer the structure of the rings, estimate the sizes and orbits of the suspected moons, and test theories of how satellites form from disks of material. This super Saturn, with its rings that could contain entire orbits, stands as a fitting final mystery. It is a reminder that the architecture of solar systems is not limited to planets around stars, but can include entire miniature cosmos orbiting a dark, wandering giant, their existence revealed only by the fleeting shadows they cast across the light of a distant sun. These colossal rings are a monument to cosmic construction, but the tools for finding them are about to become far more powerful. The golden age of anomaly hunting is just beginning, driven by a new generation of observatories and technologies designed to see the unseen. At the forefront is the James Webb Space Telescope, an instrument that is already revolutionizing our view. Its primary weapon is spectroscopy, the art of dissecting light into a rainbow of chemical fingerprints. When a planet transits its star, a tiny fraction of the starlight filters through the planet's atmosphere. Webb's immense mirror and sensitive infrared instruments can catch that faint, stained light and break it apart, revealing not just the presence of an atmosphere, but its exact molecular recipe. We are moving from simply detecting a world to tasting its sky. This means we will not just find more puffy planets or hot Jupiters, we will understand what makes them puffy. Is that marshmallow world inflated by internal heat, or is its atmosphere rich in exotic, light elements? Webb can tell us. It can search for the biosignatures of distant life, but perhaps more thrillingly, it will undoubtedly find entirely new classes of atmospheric chemistry, gases and aerosols that form under conditions impossible in our own solar system, creating weather patterns and climate phenomena we have not yet dared to dream of. While Webb probes the atmospheres of known worlds, the upcoming Nancy Grace Roman Space Telescope will find the ones that hide in the dark. Scheduled for launch later this decade, Roman is designed for a powerful technique called microlensing. This occurs when a massive object, like a star or a planet, drifts in front of a more distant star. The foreground object's gravity acts as a lens, bending and magnifying the background star's light, causing a temporary brightening. Roman will monitor hundreds of millions of stars continuously, searching for these telltale flashes. Its greatest power lies in finding the loners, the rogue planets that drift between stars without any sun to illuminate them. Current estimates suggest Roman could discover thousands of these free-floating worlds, some of them potentially Earth-sized. This will answer a fundamental question: are rogue planets a rare cosmic accident, or are they as common as stars? Each one is a frozen time capsule from a disrupted solar system, and if some are warm enough from internal heat, they could harbor hidden, subsurface oceans in perpetual night. Roman will map this invisible population, revealing a galaxy teeming with dark, nomadic worlds. The flood of data from Webb, Roman, and other observatories will be so vast that human eyes alone could never sift through it all. This is where artificial intelligence becomes the essential partner in the hunt. Machine learning algorithms are being trained to find the subtle, weird signals that traditional search methods might miss. They can look at a star's light curve and identify the chaotic flicker of a disintegrating planet, the asymmetric dip of a world with a comet-like tail, or the complex pattern of a multi-ringed system like J1407b. AI does not get tired, and it has no preconceptions. It can search for anomalies that do not fit any known pattern, opening the door to discoveries that defy our current categories altogether. It might find a planet with a transit that occurs at random intervals, suggesting a wildly chaotic orbit, or detect an atmospheric signature that matches no known compound in our databases. The strangest discoveries of the next decade may not be made by an astronomer at an eyepiece, but by a neural network that flags a data point simply because it is odder than anything else it has ever seen. So what awaits us in this data deluge? We will likely find worlds that make our current list of 25 seem almost ordinary. Perhaps a temperate gas giant floating alone in space but warmed by a powerful geothermal heart with a complex weather system of hydrocarbon rain. We might discover a rocky planet orbiting a pulsar, bathed not in sunlight but in deadly, rhythmic beams of X-rays, yet somehow clinging to a thick atmosphere. Or consider the possibility of a mega-Earth, a rocky planet 10 times the mass of our own, with a surface gravity so strong it could hold onto an atmosphere of pure hydrogen, creating a crushing, super-dense air with properties like a liquid. The ultimate anomaly might be a planet that should not exist based on the age of its star, a world so old it predates the galaxy itself, a primordial relic from the universe's first generations of star formation. The tools are now in our hands to move from cataloging curiosities to truly understanding the physics of the impossible. Every strange new world is not just a puzzle, it is a key, unlocking a deeper truth about how gravity, chemistry, and chance conspire to build planets across the cosmos. The universe has shown us its gallery of impossibilities, from diamond worlds and iron rain to wandering orphans and ghostly super puffs. Each of these 25 anomalies is more than a cosmic oddity, it is a direct challenge. They push against the boundaries of our textbooks, forcing planetary science to evolve with every new, bewildering discovery. These are not errors in the data, they are the data, screaming that our universe possesses a creativity far wilder than our most imaginative theories. They tell us that the story of planet formation is not a single, simple recipe, but a library of chaotic experiments written in gravity and starlight. Our own solar system, with its neat orbits and familiar worlds, now appears not as the standard model, but as one quiet chapter in an epic of infinite variation. This journey from the first exoplanet detection to the detailed atmospheric tasting of today is a testament to human curiosity itself, a relentless drive to look into the darkness and demand it reveal its secrets. So the next time you find yourself under a clear night sky, remember this: every pinpoint of light up there could be the sun of a world where it rains glass, or where a triple sunset paints the sky, or where a planet the density of cotton candy slowly deflates over eons. The cosmos is not just vast, it is profoundly, beautifully strange. Let that strangeness fuel your own wonder. Which of these impossible worlds captured your imagination the most? Was it the evaporating planet or the one with rings large enough to swallow orbits? Share your thoughts in the comments below. If this voyage into the anomalous has sparked your curiosity, please like this video and subscribe for more journeys to the edges of our understanding. Keep looking up and never stop asking what else is out there, waiting in the starlight to astonish us all.